So now that you have an understanding about maximas and minimas, can we do this to light? That is the ultimate question. You should be able to do that if light is a wave and if Huygens is right. So far we have proved that he is right because he was able to explain refraction and the speed of light changes perfectly. So how do we make light waves interfere that way and get maximas and minimas? Can I just take two light bulbs and do that? No, not possible, because we need coherent sources. So that's what we saw, right? The two sources were giving out same frequency and they were having a constant phase relationship. And one was cresting, the other one was also cresting. They had a phase lock, I can say. How do we get such a thing? How do we make two light sources which are locked in phase with each other? Not independent, but they're dependent on each other. How do we do that? Well, there was one scientist, Thomas Young. In 1801, he conclusively demonstrated that light is indeed a wave, experimentally. And that is what we're going to talk about in his infamous double-slit experiment. So in this segment, we are going to talk about Young's double-slit experiment. It's a very famous experiment, and this is the experiment that put the final nail in the coffin to prove that Newton's particle theory was wrong and that Christian Huygens' wave theory was perfect. And so what he tried to do is he tried to get an interference pattern. He tried to prove that light exhibits interference. And if he could get all that minimas and maximas that we talked about in the previous segments, then it's a big victory for Christian Huygens and it's a big victory for Young. But the problem is, we've discussed that we need two sources which are always in phase and they have to have exactly the same frequency, which we call as coherent sources. Okay, so how do we get these coherent sources? Well, Young was a genius. He was an inventor, also he's an engineer. So what he did is the following. He took a source, and from this source you have spherical waves that come out. And then what he did is he used a slit. Oh, sorry, he used two slits. Like so. Because when he uses two slits, remember, each point on this wavefront acts like a secondary Huygens source. And so what happens now is that one Huygens source survives, all the other Huygens sources, their waves, secondary waves, are absorbed. One Huygens source survives here and another one Huygens source survives over here. And so now these two Huygens sources act like coherent sources because these two Huygens sources were on the same wavefront before. So they are definitely going to be in phase with each other and they are definitely going to give out the same frequency as that of the original source. So this was the brilliant, ingenious idea. You would say not so ingenious. Well, it was ingenious because he was the first person to think about it this way. And this is the way in which you can get, this is one of the ways in which you can get two coherent sources. So these two coherent sources give out their secondary waves which travel out in all direction, and now these two waves can interfere with each other. And now what Young was trying to find out is, and what we are going to also find out, is if I know what this distance is, that this is, let's say, capital D, and if the distance between the two slits, we'll call it as small d, this is the standard notation that we're going to use, then is it possible for me to find out where on this screen are we going to get maximas and minimas? Where on the screen they're going to interfere constructively and where they're going to interfere destructively. So let's take some random point P. Then this wave would have traveled over here, traveling some distance. This wave would have traveled over here, traveling some distance. Now if this D is very large compared to this one, meaning that this screen is far away,
compared to the distance between the slits, then we can do some assumptions. We can say that these two rays of light are almost parallel to each other. So if I zoom in on this section, what I will get is somewhat like this. So here is that. So here is one Huygens source that survives over here, and here is that another Huygens source that survives. And since I've zoomed in on this section, it appears that these two rays are parallel to each other. So this one goes this way. Yeah, of course, they go this way. Arrow marks are important. And this one also goes this way, and they're parallel to each other. And this is the center for the reference. So let's say that this point P is it's such that this angle is theta. And remember, I am interested in calculating the path difference between the two waves, because if I know what the path difference is, then we can use our conditions for construction and destruction. The way to calculate the path difference is very easy. All I have to do is drop a perpendicular from here to there. Let me call this as source A, source B, and let me call this as some point M. Once I drop this perpendicular over here, it is quite obvious that even this angle has to be theta. Think about that. Why? So once we have that angle to be theta, then we can easily see that BM must be the path difference, because A to that point B and M to that point B, this point which is far away now, is exactly the same. So BM is that extra path that is traveled by the second source, and therefore BM must be the path difference. Therefore BM equals the path difference, which we always write as delta lambda. But we know what this slit distance is, that is small d, and therefore we should be able to calculate how much BM is with a little trigonometry. If I use trigonometry, I use sine theta for this triangle. I get the opposite side divided by the hypotenuse, and therefore BM now becomes d sine theta. And so that is the expression for our path difference. And since I now know for what path differences I get construction and for what path differences I get destruction, what I can now calculate is for what angles I get construction and for what angles I get destruction. And that is what we have to understand here. So let's go for construction. I will choose some color for this. Let me choose blue for this. So for construction, if you remember, the condition was that path difference should be an integral multiples of lambda. We will work with path difference here. So now I can say that for construction, d sine theta must be equal to n lambda. Therefore, theta must be equal to n lambda, sine theta must be equal to n lambda divided by d. But since we are dealing with, these are far away, then this angle theta is extremely small, and so I can make this approximation that sine theta is basically theta, and you get theta equals n lambda by d. And what we now have is an amazing result. This tells me for what angles I'm going to get a construction. So since n is an integral in integer, I see that the first construction I get is when n equals 0. So for theta equal to 0, I get a construction that is right at the center. When n equals 1, I get the second construction. So that is lambda over d. We call that, this is the central maxima. We call it as the first maxima. This is the central one, this is the first one. And for n equals 2, I get the next construction. So 2 lambda d by d, and so on. So nth maxima is given by n lambda d by d. So if I go lambda 1 angle up or lambda 1 angle down, then I will, if I get theta 1 angle up or theta 1 angle down, I get the first maxima. If I go theta 2 angle up, this angle, theta 2 or theta 2 angle down, I get 2 lambda d by d, and so on. That's how I get it. Let's look at destruction. I will choose green for destruction. So let's go for destruction. And from our previous segment, we saw that for destruction, our condition is that delta lambda must be 2n plus 1 lambda by 2. Therefore, now I can say that if d sine theta equals 2n plus 1 lambda by 2, I get destruction. And similarly, all I have to do is sine theta equals 2n plus 1 lambda by 2d, or theta equals 2n plus 1 lambda by 2d. So these are the angles at which I will get a minima. Therefore, the first minima which I'm going to get, which I'll call as theta 1, is when I put n equals 0. And therefore, I'll get as lambda by 2d. So at that angle, I will get a minima. The next minima which I'm going to get is when I put n equal to 1. And so when I put n equals 1, I get 2 plus 1, that is 3 lambda by 2d. And so on. Notice, because of our notations, just notice, so it's a small note that you have to do, is that when you talk about construction, for n equals 0, we get the 0th maxima, that is the central maxima. And for n equals 1, we get the first maxima. N equals 2, we get the second maxima. But when it comes to destruction, there is no 0th minima. So when I put n equals 0, I directly end with the first minima. So you have to remember this when you're doing numericals, that for calculating the first minima, you have to put n equals 0. And to calculate the second minima, you have to put n equals 1. So just a note. So these are the angles at which you get your constructions and destructions. Let's look at this in a little bit more detail now. I can now use this information and try to draw sort of a plot as to what I would see on the screen. So here's my screen. So, okay, let me just draw it bigger. So here's my screen. And let's say this is right at the center, and I'm going to put angles over here. So if I go at an angle of lambda by d, here it is, lambda by d, or 2 lambda by d, or 3 lambda by d, at these angles I end up getting a maxima. So maybe this is that point where I get lambda by d. Next, where I get it as over here, let's say that's 2 lambda by d. This is supposed to be the same distance, of course. And maybe next one is over here, that is 3 lambda by d. And I can go same distance down, lambda by d, 2 lambda by d, 3 lambda by d. And these are the places where I should end up with a maximum light. And if I go at these angles, that is lambda by 2d, 3 lambda by 2d, and so on, I should get minimas. Now lambda by 2d lies exactly in between this. That's over here. So this is where I get lambda by 2d. And 3 lambda by 2d lies exactly in between this. So green are my minimas. And this will of course be 5 lambda by 2d. I can do the same thing over here. So these are the points. This is 2 lambda by 2d. This is 3 lambda by 2d. And this is 5 lambda by 2d. And what's going to happen is the intensity, that's what I'm interested in. The intensity is going to be maximum over here. So these are maximas. So here will be a maxima. Here is going to be a maximum intensity. Here is one. Here is going to be maximum. And here, and over here, and over here. And at these green spots, I will have a minimum intensity. And to keep things simple, let's say it becomes 0. So here is 0. So what's going to happen, that intensity is going to somehow change from here to 0, maximum to 0, and it turns out it's going to be somewhat this way. It goes like this, it goes like this, it comes back like this, and then it goes this way, like this, So that's how the intensity plot is with respect to angle. Minima, and so on. So this is the center mark. So for example, if I consider this one, then this angle is lambda by d. That's what this plot is saying. If I go here, then that angle is 3 lambda by d. So it's telling me at what angles am I going to get the pattern. So you can see there's a nice pattern that you are seeing over here, and you are going to see alternate bright and dark fringes. So we call them as fringes, by the way. So alternate dark and bright bands. But what if I ask you, what is the angular width of each band, each bright or each dark band? The angular width, for example, I can consider this angle. So this is the width of the band. Or I can say this one. Or I can say this one. And you can clearly make out from here the width of the band is equal, and that is equal to lambda by d. Because you can see over here that this width is lambda by d. You can consider over here and you will see this width is 2 lambda by d minus lambda by d, which is lambda by d, of course. You can see the width over here. It's going to be 3 lambda by d minus 2 lambda by d, again lambda by d. Remember, these are not linear distances which I plotted over here. These are angles that I have plotted over here. So this angle which I have plotted over here is basically this angle. So I hope you understand what I'm talking about. Okay, so the angular width of each dark or bright band, the angular width is going to be lambda by d. That's how big a bright band or how big a dark band would look like. However, if I want to convert this into linear distances, then I have to again use a little bit of trigonometry. And that's not so hard. For example, if I want to know what is the linear width of each band, then look at this triangle. You know this angle theta. This angle theta is lambda by d, of course. And we know this slit distance, that is capital D. So if you know this and if you know this theta, then we can calculate the linear width over here, and that all I have to do is tan theta. So I can do tan theta is the opposite side, which is going to be the linear width, of course, divided by the adjacent side. And the opposite side is going to be d times tan theta. But remember, small angle approximations, so it's going to be d into theta. So what this tells you is that if you want linear quantity, it could be linear width or whatever that is, I'll just call it as linear quantity, in interference pattern in all of our experiments over here, it's going to be just the screen distance times the angular quantities. So that is something to remember. Therefore, if I asked you what is the linear width of each band, which we call as the fringe width, so the linear width, which we'll call as the fringe width, which is called as beta, it's going to be capital D times the angular width. And that is the expression for this. And what Thomas Young did was that not only did he prove he actually got this pattern, not only did he get this pattern and prove to everyone that light was a wave, but by using this, he was able to calculate what is the wavelength of light. Because look, Young was able to probably calculate what beta was just by looking at this. All he had to do is measure this, and that gives you beta. He experimentally calculated beta. He was an engineer, and he knew what the distance between the slit were, and of course, he knew what capital D was. And so out pops lambda. So all he had to do was lambda equals beta times D divided by D. And bang, he was able to calculate what was the wavelength of the light that he was using. And today we know from his today we know what the wavelength of light was, but probably what he must have calculated is that if you use yellow light, you would get the lambda, the wavelength of light, to be somewhere about 500 nanometers. So Young gets the credit for doing this brilliant experiment, confirming the wave theory of light, and calculating for the very first time in the human history the wavelength of light.